Hey,
all right. Anyway, welcome back to the video. It's like we're on TV. I didn't even say welcome back. I'm an idiot.
Did we have a commercial?
We had a commercial, guys. Welcome back. My guests tonight
Restart it.
I'll be a guest. We're keeping that. Okay, the next chapter is the periodic table, and it's really short. We'll be done with it probably by the end of next week. It's just kind of, there's no real math involved. It's more just kind of memorizing some things about the periodic table, how it fits together, some of the trends in the periodic table, and then a little bit of history here in this first chapter. But it kind of ties very well with electron configuration, which we spent some time learning last chapter, and the Beatles are more famous than me. So, properties of the elements repeat themselves as you go through the periodic table. That's why it's called the periodic table, because the properties repeat periodically. Get it? There are several similarities.
Oh, that's
it's pretty.
Gross.
We should have done that last week when it was Halloween.
Yeah, that's really kind of hard to read.
Oh, is it? Okay.
Yeah.
Why did you say that? Here yet?
We should go for a brighter
All three different parts.
Why did you say that?
We
We left the computer here.
Seriously?
Yeah,
Well, it was locked anyway, so we couldn't.
Yeah, we couldn't do anything about it.
It's okay, I'll do it.
Oh, you just don't get to do it at all?
You should have Bab talked about Will Ferrell.
Also, we just left the card in the middle of that story.
There's
There's a sledgehammer in there.
Add some cinder blocks. And sled, for
And a
that
couple
matter.
mics.
He's just like,
Some shiny stars.
I think there was like a tin hat, too.
Okay. Part of this chapter is examining how the properties of the elements repeat themselves. And so there are some similarities you'll see on the periodic table. The periodic table itself was kind of, well, the groundwork for it
there we go.
was kind of put down by a Russian chemist named Dmitri Mendeleev. He was the first person to produce the first orderly arrangement or periodic table of 63 elements known at the time. So a pretty big deal for a guy living out in the middle of nowhere in Russia. Put it together, and his work was kind of world-renowned after that. He ordered the elements in order of increasing atomic mass. At that time, we didn't know how many protons were in an element, but you could know the element's atomic mass and order them in that way. So he just arranged them from right to left, and then started a new row every time he noticed the properties repeated. So for example, if element number 1 reacted with water, and then there was like, let's say, 10 more elements that had different properties, and he got to element number 11, and that also reacted with water, he made a new row for that, and arranged them that way. And so elements that were in columns had similar properties.
And columns are the up and down.
Columns would be up and down, that's true. In his table, he actually left gaps for elements that had not existed yet or had not been determined to exist. So he said, this element doesn't fit here, so he moved it over a spot, and there was a blank spot in the periodic table for elements that were later determined. Okay, he correctly predicted their densities, their atomic masses, without even knowing what they were.
I'm blowing my nose.
I'm not saying anything. Very important bodily
I
function.
need to be able to breathe, don't I?
Can you say that without it being a lie?
What?
I'm not saying anything.
I'm not. I guess not.
I'm tired.
I guess you're right. I'm wrong. He also noticed that he was smart enough to notice that whenever he did this, was it 1869 or something, that to realize that it didn't work out as absolutely perfect as it should have. He knew that there was a better way to do it, but at the time there was no way to determine what atomic number was. And so he had a pretty good start. And as we found out more information, as science got better, as technology and tools got better, the periodic table was kind of tweaked to better represent what was going on. Okay, so 2 important things. 1, predictions. He left spots where he knew elements would be that had not yet been found. And then 2, he knew it wasn't the best way to do it, but he knew that was the best way, of the possible time. Okay, he predicted those properties, as I said, of missing elements, whether it was the density or their atomic masses. And so eventually, we could figure out what atomic number was, and that's the number of protons in the nucleus. When we arranged the atoms by atomic number, all the discrepancies, all the little minute problems with Mendeleev's table disappeared. So when we arrange them this way, order of atomic number, 3, 4, 5 through 10, new row, that sort of thing, all those discrepancies were gone. So it fits together very, very neatly, and that's what we're going to spend the chapter talking about. Mendeleev's principle of chemical periodicity is known as periodic law, which just means, like you think it means, properties of the elements repeat themselves as you go across. And so that's probably a longer definition than you want, but here it is. And the elements are arranged by order of atomic numbers. Elements with similar properties appear at regular intervals.
So did you have a girlfriend in high school?
No.
You didn't?
Haven't you seen his picture on the south side from high school?
Doesn't mean you can't have a girlfriend. I don't know. So is that a no right now?
First time I talked to girls was when I was like 23.
No, like, actually, be serious.
Is this serious?
I talked to one girl, my wife. I was like, since I'm talking to you, it means that we have to get married.
When you were
23?
23?
23.
What are you?
I grew up in a very small town
You're lying.
You grew up in a very small town of Apples Island.
with very few females. Just a different upbringing than maybe you guys are used to. I don't want to be judged. I don't want to talk about it too much. I don't want to be judged for what happened or what didn't happen.
Some random people who watch this video and be like, wow, this teacher's kind of a loser.
It's okay. There's some kids in the hall who walk by and like, wow, that guy's a loser, so.
I'm not
They don't need to see the video, right?
They're just jealous of the sport club.
Okay. The columns in the periodic table have become very important. And that's because the elements in each column of the periodic table have the same number of electrons in the outer energy level. We call those valence electrons, which I think we get to in a second, but if we don't, I will tell you. Valence electrons are very important. At least let's say valence electrons. Nice.
Whoa. You make this, you make up this, Someone, if you could be a scientist, who would you be? Well, if you could be a scientist, who would you be?
Got it? Valence electrons.
He almost got killed by a bike. Yeah, she tried to poison him, but he's a scientist, so he knew that it was
If you guys could impersonate one group of adolescents, who would it be? Freshmen, because that's how you sound right now. Let's pick an element in a column. Let's say, I don't know.
Gold.
No, in the outer columns, the tall columns.
Xenon.
Oh,
Lithium.
that's so far.
Lithium.
That's too.
Neon.
That's better. Okay, so neon.
Picky.
Neon. Its configuration, if you're writing the electron configuration for neon, it's 1s2, 2s2, 2p6. There's the configuration of neon. Okay. The valence electrons are the ones that are in the highest energy level. What's the highest energy level here?
2p.
2p. But this is also the 2s, so you got to count this too. So these two 2s, because they're the same number, this one and this one, because the energy, remember the number is the energy level. So 2 and 2. These right here are called the valence electrons because they're the ones on the outside shell. Remember that as you went up the column like this, you get further away from the nucleus. Here's the nucleus. Here's 1s, 2s, 2p, etc., etc. And so you're going further away from the nucleus. So these ones that are the furthest away and have the highest energy. We call them valence electrons.
Did we learn about this with the circles and
Yeah, you might have learned about this in freshman.
What isn't the one single electron that's the farthest?
No, well, I mean, one of them are furthest out, but in terms of energy, they all have the 2s. So we're going to count them all as electrons. And the valence electrons here have the highest energy. They are the ones that determine how a particular element reacts. Okay. This one here, if you count up how many electrons are total there. 8 valence electrons. One of that squared off. Right? So you got 2 here, and you got 6 here. Okay. How about another element like phosphorus? Phosphorus is 1s2, 2s2,
Where's phosphorus?
Oh, it's 2p6, 3s2, 3p3. 1, 2, 3.
Yep.
Where is it?
How many bits?
15.
Element number 15.
They only say the last one.
The valence electrons, again, are the ones in the highest energy level, so here, and you just total up how many there are. 2 plus 3 is 5 valence electrons.
Is it just the last two of them?
It's the last, whatever highest number. So if it just ended in 3s2,
So it's just
then it'd be 2 electrons, yeah. It doesn't always have to be 2.
What if it was whatever the one that ends in the 10?
A 10, you don't, that can be kind of dicey. So for valence electrons, I'm only ever going to ask you the tall columns here, not here, and then here. Okay, the ones that are tall columns. Those are the ones that kind of, once you start getting into the 3Ds and the 3Ps in this section here, the electrons get a little more complicated. And so we're not going to worry about them as much. But for here and on the right side, you should know the valence electrons. We call them these representative elements, the tall columns here, this one and this one, because they represent pretty much everything in the periodic table: solids, liquids, gases, high densities, low densities. It's very easy to find valence electrons. You don't need to write the configuration, although that can help. All you need to do is count the column that it's in, and you don't count the middle. So all of these, this is 1s1, or sorry, 1s1, 2s1, 3s1, 4s1. So how many valence electrons there? All of them. They end in 4s1, 1s1. Yeah, 2s1. They all end in 1, right? So this is the 1 column. This all ends in something s2, so this is the 2 column. Skip. This is 2p1, 2p2, 3. So this goes this is 3 valence electrons, 4, 5, 6, 7, and 8. Okay, and that can determine how many valence electrons. So you don't need to write the configuration. If I say how many valence electrons does oxygen have, you just go 1, 2, 3, 4, 5, 6. It's got 6 valence electrons. Okay, everything in that column. And you gotta make sure you skip. Don't count those. What else about valence electrons? Valence electrons are important because they dictate properties. All of these things, for example, react very violently with water. Okay, and that's because they have 1 valence electron that they'd love to get rid of. These will also form bases very, very well. Okay, and the reason that they have because they have 2 valence electrons. These will all react very violently to gain 1 more electron. And so there's lots of different properties here that we'll talk about as this chapter goes on, but it's all due to the fact that they have similar valence electrons. Everything in here, 1, 2, skip, 3, 4, 5, 6, 7, and 8. Except this has 2 only. This is an exception. It only has 2 electrons. Let's see. Is there something in here about? Oh, let's see. Oh, good. Okay, as I mentioned, elements with similar number of valence electrons react in similar ways. Okay, good, very good.
We done?
No. So some referring to we said columns and rows and stuff. They're called special things with the periodic table. A column is called a group, sometimes called a family if it's really old school. Elements in a group or family, get it, share similar properties.
No, I don't get it.
Well, kind of like how I'm really smart and my family Lucy is really smart as well. She now calls the goldfish Go-Go's, which is like really great.
Did you teach her that too?
Go-Go. It's the same as she also calls Ringo Starr of the Beatles. Go-Go. But that's okay. She's learning how to make hard consonants.
Did she go trick or treating?
She did not.
Why not?
Because we had our family over and she just wanted to kick it. She wanted to go outside. What's wrong with that?
What did that teacher just say?
That was a job.
I thought I was going to say tricky.
Oh yeah?
Chicka.
Did you get the treat down or
No, we couldn't get that one. The horizontal rows in the periodic table are called periods. Each element, or elements in the same period, have the same number of occupied energy levels, but they do not necessarily share similar properties. And I'll point that out in a second to you. Can I? see if I need to tell you some more things.
Don't do it.
Hold on, we'll come back.
Now we're good.
Oh god.
Time for us to do
Why is it
nothing.
so yellow?
Hold on.
Time for us to work on our speech.
No talking.
I don't talk.
Go, go.
Yeah, they're.
What's the homework?
Oh, we're not done with the homework yet. We're gonna talk some more things.
What?
We got it all enough.
We have homework?
On the periodic table, well, with this rows and periods thing, you can kind of play battleship, sort of. You know, you can say, if I say what element is in, you know, group 2, period 3, just go over 2, down 3, and it's magnesium. Okay, so you can kind of play a battleship game, which is one thing. The other thing is that sometimes you count these and sometimes you don't. There are 10 in the middle, or this is all the D block we call it, because they all end in something, D something. And so here's 1 and 2, and if I say, you know, sometimes these are referred to absolute numbers, and this is called 11, 12, 13, 14, 15, 16, I mean, it should be 18. 13, 14, 15, 16, 17, 18, and so you're counting all the ones in the middle, and sometimes, just because I refer to them by 8 as well. So like this would be 1, 2, skip, 3, 4, 5, 6, 7, 8. So just be careful of that. If I say 8 or 18, it means the same thing. Or if I say, you know, 7 or 17, it could be the same thing. You'll know when it's different because it'll make sense. But so sometimes you count all of them and sometimes you don't. It just depends on my mood and what we care about. For the most part, though, we're going to kind of ignore the middle part and talk about elements and the representative groups.
So
When are we gonna learn about the middle part?
colonium, is that part of the middle?
Yes, colonium. Oh, yeah, so this part here.
No, I'm talking about, see how it stares down?
Oh, yeah. We'll count these. Well, it gets tricky there. This line, which we'll talk about, I guess, later, earlier next week maybe, separates metals from nonmetals. And so all of these are metals and all of these are nonmetals. Technically, if I say, you know, technically when we say this right side, we're talking about this like very corner here. And we don't like count them, but
So those are part of the middle, right?
technically. But sometimes I'll use them as marking out the middle. You'll know when. Like if I say how many valence electrons does germanium have, I'd probably just go count and you would say it's 4. And for the most part 4, and for the most part it works out. Yeah, it's good.
Then we're gonna learn about the middle.
We'll learn about the middle later, but not now.
Is it tough?
Is it tough? No, not really.
Why?
Because I don't want to.
So you just dictate what we learn?
So I hate what you learn.
You dictate it.
Oh yeah, I dictate it. Yeah. It's great, isn't it?
Yeah.
You can represent the valence electrons of elements by something called Lewis structures. Lewis structures are very simple to know. You just write the element and then write some dots and how many valence electrons it has. So for example, let's take an element calcium, something simple. Okay? How many valence electrons does calcium have?
I got 5 2.
2 valence electrons. And how do we know it's 2?
Because it's second over.
Second column. Okay. So when you want to represent that with a Lewis structure and show how many valence electrons it has, you just draw the element and then two dots. Doesn't matter what side you draw the dots on, but kind of imagine this as having a little square around it, so you have 2, 4, 6, and 8. Because nothing's going to have more than 8 valence electrons, right? So if I said draw the Lewis structure for like bromine, how many dots would you draw for bromine? Right side.
7.
7 dots, right?
Yeah.
7 columns. So 1, 2, 3, 4, 5, 6, 7 dots. Okay, that's called the Lewis structure, and it shows you how many valence electrons something has in a picture, which is very nice. Okay. The important part is the magic number is 8. Everyone's very happy when they have 8 valence electrons. We call that a full octet. So 8 valence electrons. 8 valence
Argon.
is a full octet.
Do argon.
Does that have to do with the oxidation state?
Sort of, yes. For example, argon is all the way on the right. And that column's got a special name, which we'll talk about
Noble gas.
tomorrow. Very nice. Argon's got 8 valence electrons. When you have 8, you're full. It's like you just ate turkey dinner, Thanksgiving dinner. It doesn't always involve turkey, but whatever.
Yeah.
These elements that have 8, they don't react very well. They don't make lots of compounds. They don't do much. They're very content to have 8 and be by themselves. That's why they call them the noble gases, because they don't really react with that much. There are some compounds, but not very many compared to the rest. Everyone else is trying to get to 8, and there's 2 ways to get to 8. You could either gain electrons, like chlorine has 7. It would love to get 1 more valence electron. Or you can lose electrons and drop down to 8. Like for example, sodium, it's got 3s1. But if I got rid of that 3s1, let's see where sodium is. Let's draw here. Sodium is 1s2, 2s2, 2p6. If I got rid of that 3s1 for sodium, how many valence electrons would I have, right? Here's my 2 that has 8. Okay. And so, everyone, wait, what happened? You're talking.
Sorry.
Everyone's trying to get to 8. That's the goal. Either you lose or you gain to get to 8. That's the bottom line. 8 is the magic number for this particular chapter.
We were
No,
discussing
no explanation.
covalent and ionic bonding.
Just the
Okay.
apology is all that I require.
There's a question.
We actually have a question.
Please go ahead.
What's the difference between covalent and ionic bonding?
Great transition. The next chapter is actually ionic bonding.
Okay.
And that has to do with how you share electrons. Covalent bonding, you share electrons between. Ionic bonding, you transfer electrons back and forth. So there's not sharing, but it's more of a give and take. Great question.
Sums,
I
why
don't
do
know,
you
is there more
circle
you
those
say?
things? No. Aren't you a blower minds?
I just did.
Aren't you gonna blow our mind?
Yo, sums.
Yeah.
Why did you circle that 2s2 and 2p6?
Oh, because if you get rid of the 1 here, the goal is to get to 8, right?
Yeah.
And so, well, there you are. If you, I feel like I'm like a ringer or something, you know? Just like, yeah, I don't know what's going on. Anyway, so, you can either do 2 things to get to 8. You can gain 7 more, which is a lot, or you can just drop this one, and then you have 2 plus 6 is 8. And so, they're going to get to 8 however the easiest possible way is. Things that are really close, like chlorine, has 7. It just needs to gain 1 more to get to 8,
Right.
so it's going to. These will get rid of, that's how bonding happens. And this would love to get rid of 1, and then you kind of have this perfect storm situation where sodium, like for example, let's talk about sodium fluoride, which is in your toothpaste. Russia, Russia, Russia. If you get rid of, if this one wants to get rid of 1 electron, and fluorine wants to get 1 electron,
Bubbles.
they're in love, right? Yeah, they bubble. I guess I don't know. But they are in a happy relationship where you can give this 1 electron to fluorine and you make a bond, and then say you get sodium fluoride, which we're kind of setting the table for next chapter.
Covalent bond.
So they're married?
Ionic bond.
Dang it.
Yes.
What does hydrogen do?
Hydrogen's kind of in its own special case. Okay? It loves to get rid of that 1 electron it has to form compounds, but it's kind of like in its own little world.
What are you doing now?
Do you have other questions? No.